Hi class, I wanted to do a quick review of the definite integral, which stems from the fundamental theorem of calculus. This is exactly like the previous video in the sense that we got to do some type of integration, but then there's an extra step of plugging in what's called the bounds of integration. Anyways, here's the fundamental theorem of calculus. All right, if f is a continuous function on some closed interval from a to b, and look down here, we have a to b here, it's different from the previous examples. All right. And f is the antiderivative, if capital F is the antiderivative of lowercase f, then if we're going to integrate, we say from a to b, these are our bounds of integration, lowercase f of x dx. Well, we know how to integrate the lowercase f of x to get the antiderivative, but then we evaluate from from a to b. Well, what you do is you take the value of b, you plug it into the antiderivative, then you subtract, you take the value of a, and plug it into the antiderivative. All right. You guys should have seen this at the end of Calculus 1. Should have been one of the last things you studied. So this should definitely be a review for you. All right. So by the fundamental theorem, we can evaluate this type of integral. All right. The integral from a to b of f of x dx easily and exactly. All right. All you have to do is just like before, find the two antiderivatives. You have to find the antiderivative of f of x. Plug in b and then subtract in when you plug in a. I'll do three examples, simple examples to walk you through it. That'll help remind you how to do them. All right, but first let's go over some of the properties. All right, if you integrate from a to a, so that would be like from 1 to 1. Obviously that's 0 because you're just on a straight vertical line. All right, if you switch the bounds of integration, so if you go from a to b and then all of a sudden it's from b to a, it's the same thing with the negative. All right, so think about like negative does the opposite, so this makes sense. All right. Just like with the indefinite integral, you can factor out a constant if it makes solving the integral easier. But if you do that, just remember to multiply the constant back at the end. All right. The sum and differences work as well. So if you have the definite integral from a to b of two functions, you can do it as two separate definite integrals. And then finally, if you have the integral from a to b of f of x, if there's some value c in between a and b, you could go from the integral from a to c and then from c to b, all right, as long as you added them back together. All right, but we'll mostly concentrate maybe on this one, the fourth one here in our third example, but pretty much just the traditional fundamental theorem of calculus. These are just some interesting little tricky rules to help you remember. All right, so let's do example 1. Suppose I want to integrate from 0 to 3 x squared dx, right? This red box here, what I'm going to put in here is I'm going to put the graph so we can see exactly what we get. All right, if you remember, the fundamental theorem of calculus gives us the area under the curve, so the area under x squared between x is equal to 0 and 3 and above the x-axis. Okay, so all I have to do is apply the general power rule and get the antiderivative of x squared, which is x cubed over 3. And then I'm going to plug in 0 and 3. So I'll start with 3. I plug in 3 and cube it, I get 27 divided by 3 is 9. Plug in 0, 0 cubed is 0 divided by 3 is 0. So 9 minus 0 is 9. So you can see what exactly is going on here. This is the graph of x squared. All right, this is only a part of it, and just in the first quadrant. And what we're saying is the area from 0 to 3 above the x-axis and below the curve, so this black shaded area here, is equal to 9. All right, that's what the fundamental theorem of calculus gives us, the area under the curve. All right, let's do another one. All right, let's integrate from negative 1 to 1 e to the 2x dx. Well, if you look back in our first lecture, e to the 2x will integrate as e to the 2x over 2, or 1/2 e to the 2x. That was just a direct application of the formula I gave you. So what we have to do is then we have to plug in 1 and subtract away when we plug in negative 1. Well, if you do that, you plug in 1, you get e to the 2 over 2 minus e to the minus 2 over 2. If you plug that into your calculator, you'll get this. And you can see here, here's what the graph of e to the 2x looks like. So between negative 1 and 1, that's your area. Boom, we got it. All right, let's do one more. So this is just a combination of the two. All right. So here I'm going to integrate from 1 to 3, x squared plus e to the 2x dx. All right. Obviously, we saw x squared integrates as x cubed over 3. E to the 2x integrates as e to the 2x over 2. So here's what I have to do. I have to plug in 3 into this, and then I have to subtract away 1 plugged into this. So be very careful and watch how I have it here. So 3 goes into this, I get 9. 3 goes into this, I get e to the 6 over 2. Minus 1 goes into this, I get 1/3. 1 goes into this, but then I'm minusing it, so I get minus e to the 2 over 2. And that, if you just plug into your calculator, will equal that number. All right. You can use your calculator for a lot of these as necessary, or you will need to use your calculator. Obviously, you can't do this in your head real quickly. And you can see the integral here. We have the graph of it from 1 to 3, and indeed that is the area under the curve. All right, so hopefully this was a quick, easy reminder for you guys. Your homework this week will involve you doing a lot of these, and there'll be some trig ones in there too. So have your textbook handy, any notes that you may need, and you can feel free to ask me any questions in the forum. Thanks.